Good afternoon, everyone. Welcome to the afternoon session of the second day of the conference. So we are very happy to have Andreas Damianou and Neil Lawrence here today, who are the recipients of the AISTATS Test of Time Award for their paper Deep Gaussian Processes. Now, the Test of Time Award is given to a paper that was published 10 years ago at AISTATS. And so in this case, this is AISTATS 2013. And back then we had a grand total of about 70 papers, of which 6 were published as notable papers. And what I think is interesting is that, this work by Andreas and Neil was actually not amongst these papers. And I guess this serves as a lesson that it's very difficult for current committees to predict future impact, right? By now, however, I think the impact of the Deep Gaussian Processes work has been kind of undeniable. Andreas and Neil's work showed how it was possible to stack Gaussian processes into kind of multiple layers in a way that's kind of, I guess, established a connection with deep learning. And this has been a very influential idea, and it's inspired a host of follow-on work. And the paper continues to be cited to this day. So Andreas and Neil, why don't you come up here? We have some certificates for you. Let's all congratulate them on this well-deserved award. Sorry, so we're going to take a quick moment to pose for a couple of pictures, and then they will give their talk. Yeah? Yeah? All right.
Which way?
Maybe the gentleman in the center?
You guys at the middle?
You doing like that or like this?
All right.
Every day can be a better day despite the challenge. All you gotta do is
All right.
leave it better.
Stage is all yours.
So I'm going to start, and Andreas is going to take over. I'm going to do the emotional, teary bit, where you sort of state what an amazing privilege it is for your absolute favorite conference to have given you such an award, and to get it with one of your amazing students. All students are amazing. So there's this sort of question like, how do you deal with such awards? What should your talk involve? And Andreas is going to actually do some of the review of the technical ideas in the paper, but what I'm going to do is just set the context a little bit for the background to the paper. And I want to do that by going back to how I got into machine learning. So I was a mechanical engineer as an undergraduate, and my first job after school was working on oil rigs, and this is the actual oil rig I worked on. It's called the Trident 14, and I was on that rig in 1995 in Liverpool Bay, which is, I think, where that picture's taken from, as it was drilling in the Lennox oil field. And there was no internet, and there's a lot of downtime on oil rigs, so I used to read The New Scientist. And I don't know if this is exactly, I found this cover from the period I was on the rig. This is New Scientist from December 1995, and it's saying, machines with a spark of genius. And there were a lot of articles in these magazines about these new phenomena called neural networks. This one, I looked at this one, and this one is about, apparently machines one day will actually be creative. You won't believe it. So I knew I didn't want to spend my whole career working on oil fields. I enjoyed engineering, I enjoyed solving problems, and the reason these two things come together is because we were doing data acquisition from the rig. So actually, this is a picture of the plan of that same rig. So this object here was my logging unit, and this is the drill floor, and I used to run a cable from here to here and acquire data from the oil well. And I used to sit next to a geologist who would interpret this data, and I would think to myself, oh, I'd like to learn how to interpret that data. And I'd ask them these rules about how to do it, and then I would try and do it. And they said, no, that's an exception. And it sounded to me like these neural networks were this really interesting technology that could perhaps capture and emulate what this geologist was doing. And so that's how I ended up going to do a PhD. Now, this picture is a picture of me in 1996, August 6 or 7. It's the Machine Learning and Generalization Summer School that was held at the Newton Institute that year. And the reason why I want to bring this in is because one of the themes that I want to highlight here is community. And what I found when I joined the neural networks community, as was the connectionists at that time, was not just a set of really interesting ideas, but a set of really interesting, welcoming, intellectually lively people. And I got to go to that meeting, and I got to hear Jan LeCun talk about convolutional neural networks, LeNet 5. I got to see Jeff Hinton talk about what he told us was the way the brain worked, and it was something called a hierarchical community of experts. Something I learned then is the first time Jeff Hinton tells you how the brain works, right? That's the time you really believe that that's how it works. The second time, you're a bit disappointed he's not still sticking with his story the first time, but you never forget the first time Jeff tells you how the brain works. And that's where I heard how the brain works. Hierarchical community of experts, Brian Salons and Jeff Hinton. What I also found out there is I was hearing about all these sort of very interesting new models. I mean, so it's funny, I live and work in Cambridge now. This is how the Newton Institute looks now. My hair's shorter, but the trees are taller. So that's 25 years ago. But it made a very, very strong impression on me, the quality of this meeting that I attended. And I think the thing I want to emphasize about this paper is that it's not a paper that exists on its own by some idea that Andreas and I came up with. It sits within a broader scope of community of people who worried about ideas or agreed something was interesting to work on. And very quickly, I myself sort of got into that. Because one of the things that was presented at that meeting, and I'd been all into to neural networks, was this new method of Gaussian processes. And it was very apparent that Gaussian processes were the future. And that neural networks were just not going to be the way of doing things because of all these interesting qualities of uncertainty representation. So obviously, I think most of this audience understand a Gaussian process. This is a Gaussian process interpolating through 3 data points. And of course, we're showing samples from the process. But the remarkable thing about the Gaussian process is you can do this quite complex Bayesian inference with very high dimensional integrals just through linear algebra because of the properties of the Gaussian. And that was mind-blowing to me because that is absolutely the right way of solving the problems I was worrying about on the oil rig, right? No other way. In fact, they're very widely used in geospatial modeling, of course. So I was quite surprised sort of 1 year later when David Mackay, who was also in Cambridge, I met him for the first time at the Newton Institute, he gave a tutorial at the Newton Institute as part of that 6-month program that was led by Chris Bishop, but he also gave a tutorial at NeurIPS that year. So it must have been 97, actually. And this is his write-up of that tutorial, where he sort of said, according to the hype of 1987, I like the fact that it's the hype of 1987, neural networks meant to be intelligent models that discover features and patterns in data. Gaussian processes, in contrast, are simply smoothing devices. How can Gaussian processes possibly replace neural networks? What's going on? And of course, David, in 1997, is actually predicting what the problem is with such models, that they aren't extracting the type of features we need. So they're brilliant interpolators, Gaussian processes, but what we're getting with deep learning is the capability to create a landscape within which to interpolate. And that's really interesting. So there's a number of people that sort of influence thinking on this, my own thinking on this, including Jeff Hinton and others. But a large part of that was a community that we started to form around these methods, and this was an early workshop. This is the first workshop. This is why PMLR exists, by the way, because I wrote to Springer saying, would you publish this workshop? And they wrote a really snotty email back. So I wrote to Leslie Pack Cabling saying, can I start proceedings for machine learning conferences? And she said yes, and this is the first. So again, community comes up again, that we got together a bunch of Gaussian process people. I actually had to reconstruct this website. It doesn't exist anymore, but I found the HTML. To sort of show what the websites looked back in 2006, to get together and discuss the challenges of deploying these things in practice. Because something that always stuck with me, and I realized only about 10 years ago, is not the same thing for most machine learners, is I was interested in machine learning for solving problems. So I had a set of problems on an oil rig, and I was interested, can machine learning help solve these problems? So this workshop itself, Gaussian Processes in Practice, is trying to reflect that. And I was really enjoying Shakir's talk this morning when he basically was talking about the same thing. And he was talking about that dynamic interactions between the problems you solve and the way they affect society, and the way that society's problems should affect the way you think. And that, to me, has always been at the heart of the way that I was approaching machine learning, which is why that meeting was about how you deploy Gaussian processes. Shortly after that, a book came out, which I think was a really massively important thing for the community, a book that summarized the knowledge the field had so far. And I put it alongside Thomas Kuhn's book on the structure of scientific revolutions, which is a 1960s book that talks about paradigm shifts in science. And it talks about how those paradigm shifts, up until the 19th century, used to be represented by the writing of individual pieces of scientific work, like Newton's Principia. That changed the way people thought. And then he reflects the fact how in the 19th century, that shifted to textbooks. So current thinking was reflected in textbooks that were being used to teach. And then I was wondering what represents a paradigm today. And I was thinking to myself, more than anything else, a community represents a paradigm. And where textbooks emerge, they're just the observed variable from the latent space of what that community is thinking and doing. And that's why it's so important that we're all together here today talking about these ideas. And that's why AISTATS itself is such an important conference, because the other thing that sticks in my mind from this period is that the first paper, then Andreas will go through this history a little bit, that fed into this work, which was on called Bayesian Gaussian Process Latent Variable Models, was actually published at AISTATS 2010. And that's an important AISTATS for me because that was the first ever one in Europe. And we brought the conference to Europe explicitly, a group of us, myself, Bernhard Schulkopf, and others, to make sure Europe had access to that community. And the 2013 is actually the American edition of the conference, but I'm really pleased that we're doing this one in Europe, so I can sort of mention that. Because, of course, communities are spread across the world, but it's so important to have something locally. And when we think about that, let's not forget that there are still many continents that don't have access, easy access, to the type of capability and meeting that we're having today. So with that, I'm going to pass over to Andreas, who's actually going to start sort of saying, so I'm saying, oh, we were just all having fun together, and Andreas will talk a little bit about the technical side of the work.
Excellent. You will see more of Neil in the end. He has some slides. Before proceeding, I want to make a small parenthesis to say I'm very grateful for this award. AISTATS is also my favorite conference, and this particular work is very much in my heart. It's the basis of my PhD thesis. Also, I'm very grateful to Neil. I did this as part of my PhD. I loved your presentation, by the way. I didn't know exactly what you would speak about. It was a bunch of photos that I saw in the slides, but amazing. So in the spirit of the things that Neil talked about community, the group effort, and so on, my bit is going to be a little bit more technical, but I'm also going to speak about all the related ideas to deep Gaussian processes, what came before, what came after, and explain these things a little bit. So I'm not going to do an introduction to deep Gaussian processes. There is plenty of tutorials out there, but I'm going to do a bit of the lazy, quick introduction just for those that are not familiar. And this is by starting with a neural network, which I have here on the left. You have some inputs, x. This goes to some nonlinearities. And there is some weights that have single value parameters that one optimizes. And with appropriate multiplications, you get the output. Now, a Bayesian neural network, one can think of it as replacing these fixed parameters with distributions. And going from neural networks to Gaussian processes can be thought of looking at the limit of infinite units. So intuitively, one can think about functions as being infinite dimensional vectors. So having infinite units here, we obtain a Gaussian process, which is basically distribution over functions. And the inference is also done directly in the function space. So notationally, we say that f has a Gaussian process prior, depends on a kernel, which is a nonlinear function acting on the inputs. And this observation about the limit properties was first done by Neil in 1995. Since we agreed that we are now talking about functions, I will also use the notation where f is the instantiations of f of x in particular data points, or we can just say that between inputs x and outputs y, we have a function f. Right. So a deep Gaussian process intuitively is easy to understand. We can just say, well, let's stack these things one on top of the other. So we have now x to be our input, and we model this by saying f of a, f of f of f of f, and so on of x, where each f is a Gaussian process, is a stochastic process. So that's what we initially talked about in our AISTATS 2013 paper. These H1 and H2 now, we can call them intermediate layers, bottleneck layers, latent variables, and so on. Basically, they are the noise-corrupted outputs of each layer from the previous GP that feed into the next Gaussian process. Now, the motivation around that is that we want to relax assumptions of global smoothness that comes with a single-layer Gaussian process. One can see that in this plot here. So we have a step function. We have some observations from the step function. We can use those as training data. Is this little x's here. And we have observations only on 0, on y equals 0, and y equals 1. With a single Gaussian process, obviously, that's very hard to model because they are global smoothing machines. So if we take samples from the posterior that I represent as semi-transparent red dots here, we see that these samples are all over the place and predominantly in between 0 and 1 because of the way that they smooth the space. And if instead we use a deep Gaussian process with 1 or even better with 3 layers, we can see that it learns very well this non-stationary and particular, let's say, structure in the data. So the 3-layer deep Gaussian process model learns that there is like data in the y equals 1 and 0 regimes with very few or no jumps between. Of course, that's all easy to say when about constructing the model, but the tricky part is about propagating uncertainty, which is crucial because Gaussian processes are stochastic processes, and a deep Gaussian process has to be a composition of stochastic processes. So propagating uncertainty is crucial, otherwise we just don't have a deep Gaussian process because it's not stochastic anymore. But that's not easy to do because, as you know, if we have an input distribution, which is a Gaussian potentially, and we pass it through a nonlinearity, which is the nonlinear kernel of a Gaussian process, then the output is very much non-Gaussian, and it's in fact difficult to infer. So it's crucial to tackle this issue before we start talking about deep Gaussian processes that are actually stochastic, composition of stochastic processes. I will come back to that in a little bit, but the high-level idea is that in our work, we used advances from the interpretation of inducing points as variational parameters. So before getting to that, what is an inducing point? So if we have the inputs h and the f to be the f of h outputs modeled as a Gaussian process, which is here at the posterior shown as a blue line with associated uncertainty, then because we have a distribution over functions and we can do like posterior inference, we can fantasize as many inputs and outputs we want. And we can say that h tilde and the corresponding u is just one pair of those. Now, this initially has been part of the inducing point literature where people were trying to speed up Gaussian processes, but it has been shown, and we have used them in the Gaussian process context, that we can use those to induce tractability. So with inducing points, the information in the f of h is compressed in these variables u independently of h. And h is this tricky part that in the deep Gaussian process has uncertainty from the other layers. So in this way, we can do basically uncertainty propagation. Let me speak a little bit about how we reach this point and what is the related ideas that come before that. I don't have a visual effect. You can imagine it if you squint a little bit. So there is 2 lines of work roughly, right, that have led, in my view at least, to deep Gaussian process and what came after that. One is around modeling, or one is around approximations. So since 2003, potentially even before, people were thinking about warped GPs, where in this particular case, the outputs of the Gaussian process are warped nonlinearly before going to a regressional classification layer. And then Neil Lawrence, 2004, introduced the Gaussian process latent variable model, which was yet another important modeling milestone where we say, well, the inputs can also be unobserved and can be inferred. And these would be latent variables in that case. And even since 2007, there was like this idea, well, let's stack GPLVMs. But in that case, there was no assertive propagation. That was a hierarchical GPLVM. At the same time, there was also inducing points for sparse GPs literature. It was very rich, many approaches. I have just a sample here. But in 2009, Titias showed that the inducing variables can also be interpreted as variational parameters. And this led to the Bayesian GPLVM in 2010 that Neil already talked about in AISTATS 2010, where the idea was like, we can get a new model, the Bayesian GPLVM, because the inputs now are unobserved, and they can have a prior distribution, and we can propagate this prior distribution through the nonlinearity of the Gaussian process by using basically the trick that I mentioned here that has been introduced in the Bayesian GPLVM. So after that, soon we built basically on this trick to promote the literature and to reach to the point of deep Gaussian processes, and many other works that followed that focused on scalability and even more importantly on various approximations, how to make the approximations better of propagating uncertainty. We talk about reducing points. Technically, the graphical model will look a little bit like that. And depending on how we treat the variational distribution on U, because we do variational inference, as I mentioned, the inducing points are treated variationally, we can have distributed computations, which is shown in these two papers from 2014, or we can also have fully parallel inference in the style of SVIGP. SVIGP is a milestone, in my opinion, for Gaussian processes because it showed how to do fully parallel inference Gaussian processes. And by combining the ideas that I discussed so far with the SVIGP ideas, one can also do parallel inference in deep Gaussian processes. As I said, there was a lot of work on various approximations for deep Gaussian processes. I don't have time to speak about all of those. I actually gave a keynote in 2017 about this topic. But you can see it ranges from amortized with neural networks, EP, and other things. I want to particularly stay on this specific approximation. The paper was not only about the approximation, but let's start with that. It was Hugh Salim-Ben and Mark Dazenroth's paper in 2017, where the idea is that we can actually sample through posteriors on the function chain, Q of f for all the f's in all the layers, where f is a GP, to maintain a layer coupling. So without going into the details, the variational posterior would look something like that. And as you can see, we don't have these problematic terms h, which is these latent variables that have asserted on their own, and they're the noisy corrupted intermediate outputs. These we can call them bottleneck layers, and they need to be normally initialized. We need to put a variational distribution of those that is initialized, but here we don't need to do that. Of course, this can sometimes have trouble with modeling heteroscedastic noise because in that case, there is no noise intermediate output, and this can be shown in these plots here, the doubly stochastic variational inference of this paper with the originally proposed mean field inference. This can be fixed potentially by including noise variables as addition or concatenation. But the important point that I want to say when it comes to this paper is that it makes the model more practical, and it has been a very popular approximation choice for the software that have been built for deep Gaussian processes. Because we don't have these bottleneck layers, and we don't have the variational parameters that come with that, we don't need to initialize them. And this made the approach very practical, and when it comes to a function approximation, the authors also showed in the paper that it beats various regression classification baselines and so on. In my view, from here also, one can imagine two general lines of work. One would be more around emphasizing the latent variable aspect with all the intermediate latent variables and so on, and the other would be focusing on the function learning, or combinations of both. But I want to differentiate to point out that one could envisage also a case where we have used domain knowledge to construct a deep architecture, where intermediate, observed, fully observed, partially observed layers are stacked accordingly to what we think makes sense from our domain knowledge, and then use Bayesian deep Gaussian process inference to compress in these latent variables, distill information about all the observation spaces. One could think about that as being a nonlinear deep multi-view extension of factor analysis. So we'd have these factors that nicely contained in them segmented the information from all the different modalities of the different observations we have put around the layers. So I think this is very powerful. And going back to the software and linking to what Neil was talking about related to the community, it was really nice to see the community embracing the idea and wanting to experiment with deep Gaussian processes. People build their own packages. Some of those became very popular. So here I show just a selection of software built for deep Gaussian processes. The first three, I think one could say they're a bit closer to parts of general probabilistic programming languages. GPFLAX in particular is an interesting one because it's, in my view, it looks a little bit like a probabilistic programming language based on deep Gaussian processes. And talking about applications, there is a variety. I don't have time to speak about everything. But in this slide, I tried to group a little bit what people have been doing in practice with deep Gaussian processes. One can see that in engineering and in disease identification, there has been a lot of activity. In my view, this is because deep Gaussian processes allow the modeler to bring in their domain knowledge and allow them with very few data to learn to perform training in these scenarios, which is exactly the scenarios that appear in engineering, in disease identification, and so on. Here's an example where people have used, that was Benson and al. Actually, have used deep Gaussian processes to model hurricane structures. The original data is shown here, and the Gaussian process with one layer struggles because of the smoothness, but with a deep Gaussian process, the authors explain how layer 1 captures low frequencies, while layer 2 focuses more on the hurricane structure, and the combination gives a relatively accurate prediction. This is from our paper in 2018, where deep Gaussian processes have been used for multi-fidelity modeling. And here I want to make the point also that the way that ascent propagation works in these Bayesian models also allows to learn in situations where maybe normally with machine learning it wouldn't be possible with the existing tools. In this case, with deep multi-fidelity modeling, we show how modeling of infection rates can be done. So the high-fidelity data would be few samples from this figure here, which is 2015 infection rate data. And because we can assume that in a realistic scenario, we have very few of those observations because they're hard to gather, which are the red points here, we can complement those with low-fidelity samples, low-fidelity observations, which we can assume that in practice we can have many of. In this case, we can consider that from 2005, we have a lot of observations. So we can combine learning a function from the high and the low fidelity data through the deep multi-fidelity approach, and you can see that we get a relatively accurate reconstruction in the high fidelity space. There is a lot of derivative and related models. Again, I don't think I have time to speak about all of those. There is things like recurrent deep GPs, convolutional deep GPs, deep GPs over graphs. Recently, I also saw a paper about connecting deep Gaussian processes to transformers. It's a non-exhaustive list, obviously. Let me see how I'm doing with time. Yes, I'm almost there. So now there is a question, what does depth buy you? I talked a little bit about hierarchical feature learning. Basically, how can we introduce feature learning in Gaussian processes, which, as David McKay argued, it's like throwing the baby out with the bathwater if we go to the infinite limit, because then we just obtain a smoothing function. So limit properties can help us study these models. So David Mackay, as I said before, showed that if you have a neural network with one layer, you can imagine the first 3 nodes here to be a neural network. That's equivalent to a Gaussian process. If we imagine the bottom 3 layers to be a neural network with one layer, that's, again, of course, a Gaussian process. So what happens if we consider deep neural networks? Are they deep Gaussian process? Well, it turns out that no. In 2018, it has been shown by Lee et al. And Matthews et al. That even deep neural networks, in these limit properties and some other mild assumptions, also converge to Gaussian processes. So in a sense, a deep neural network can converge to the Gaussian process, but we know that a deep Gaussian process is a more general class of functions than Gaussian processes. It's not a Gaussian process anymore. So we need to understand what is this extra bit that we get. There has been work on theoretically analyzing deep Gaussian processes. One key insight that has been showed by Damianou et al. And Dunlop et al. Is that the degrees of freedom reduces across layers for very deep models, but for deep Gaussian processes, this can be fixed through some structural changes. And here we have, again, the Salim-Bedi and Damianou paper, where they use identity mean function, or can connect the inputs, the top-level inputs to every intermediate layer. And there is also ergodicity analysis. So Dunlop et al. Made the observation that the deep GP samples can form a Markov chain across layers. So you can study the ergodicity and also can do convergence analysis. Basically, when do we stop gaining benefits by adding more layers? There is Pack-Bayesian bounds, and also recently, Tutor-Duar et al. Showed that we can build a deep Gaussian process layer with a mean that resembles exactly a neural network layer. So that's a really nice equivalence. So I pass it back to Neil. Thank you.
Thanks, Andreas. And I was just thinking that as well as this award, which is sort of like formalization, I was feeling a little bit emotional just sitting there. Because I think the thing that we can almost feel most proud of is when we see that our work has been picked up by people we really respect, and those people are building on it. And to me, that's one of the most exciting things that you see. And it was so nice to sort of see Andreas summarizing all those people. But part of that, I think that the story doesn't finish there, because the question is, how do you forge new communities around those groups? So one of the things that we did in 2000, well, the origin story of this is that we went to Columbia in 2013 with the Gaussian Process Summer School, and then we started teaching it in Sheffield in 2015. And this, again, was about community forming, getting people together who had sets of problems, who wanted to use these tools. I had a sort of epiphany moment in 2013, cycling home in Sheffield, that if I just stopped developing new methods and just tried to teach people about existing methods, that might be a more useful use of the second half of my career than trying to invent a bunch more methods. That's probably continuously true. And so the Gaussian Process Summer Schools was sort of an example of that. But I think that there was also a sort of an awareness, and they're still going. The 2023 will be hosted in the University of Manchester, being run by Maurizio Alvarez. And the thing I love about them is they are trying to bring the applications together with the methodologies. So you can see the theme that's emerging from Andreas's work and Andreas's talk is the ability, through this sort of decomposition of algorithm, people worrying about inducing approximations, how to propagate the uncertainty through, with the flexible possibilities of Gaussian process models that allow people to express their understanding of a problem, transferring all the way to application, so that you're going all the way and bringing a community together in the way that Andreas brought those threads together. But at about the same time, I certainly feel that people like David Mackay and many of those others who were a great inspiration for me were a real reason that I worked on these things. And we were very inspired by work that Ernest Mwaze and John Quinn were doing in Uganda, doing machine learning and data science in the deployed field. And my postdoc, Shiramania, returned to Kenya. So one of the things we next did, Andreas and I went to Kenya in 2015 with Shira and John Quinn and others who'd been working on some of those projects to start a set of summer schools that were formed along the same lines of Gaussian Process Summer Schools that is now the basis of Data Science Africa. And I should say, none of us are involved in it, in the administration of it now. What we did is we helped teach and understand how you can build a community. And now that community has its own legs and runs itself, and I'll be going again in May, but I go as a participant to enjoy the community rather than, because once you have a community like that, you start realizing the sub-problem sets that they generate are far more interesting than anything one would go and tell people to generate, because there's so many interesting things about the African ecosystem in terms of lack of existing infrastructure means that data-driven solutions can do an enormous amount more to bring benefit in health and agriculture and all these areas. So that in itself became very inspiring for us, because one of the bottlenecks that we noticed was that the challenges people face in that ecosystem are not around implementing a particular machine learning method or implementing an app on a mobile phone, but they tend to be the challenges around systems. So at around that point, shortly after that, Andreas and I went to Amazon, and we continued to work on these methods there. But a major reason for going was to try and understand how you build and deploy large-scale machine learning systems at the time. This is using a deep Gaussian process to do the thing it's just doing, which is transferring from vertical lift to horizontal lift. And the reason it's doing that is the multi-fidelity approximations that Andreas was talking about can be used within the context of, and we've also done this with Formula One teams, within the context of combining simulation from wind tunnel data with simulation from computational fluid dynamics with actual flight data to get an improved picture, much like you saw Andreas showing with the disease modeling in sub-Saharan Africa, to get a better understanding of how something should perform. And in these type of test scenarios, you're often very limited on the amount of data you can acquire. If you have an enormous amount of data, you can just knock yourself out, use a deep neural network, whatever, and we definitely also did that. But as I say, the main reason for going there was to try and, oh my goodness, starting all over again. The main reason to go there was to try and understand what the solutions were. Oh. Right. I have to click off the side. There we go. Main reason to go there was to try and understand how are people deploying these machine learning systems at scale. Because as I say, the challenge you saw in the African ecosystem is not to do with can a bright student pick up a machine learning model, acquire a data set, pull those things together. It's how do you put the whole thing together to provide a machine learning system? And this is exactly what Shakir was talking about this morning in terms of runtime validation of these things. And I think one challenge we face as a community is we do not talk about this enough. Because in order for these things to be useful, they have to be deployed in practice. So you might think that companies like Amazon have all this solved. They do not. And unfortunately, they're not looking at the right time frames in order to solve it, because large companies tend to be quite short-termist in their deployment. In academia, we don't tend to find this exciting because it tends to be things like good software engineering, good systems design, so we don't tend to get publications out of it. But so since coming back to academia, the main focus of the group has been on how you deploy machine learning systems. And you might think, well, what's that got to do with deep Gaussian processes? Well, one of the major things we're interested in is if you do have an existing system where you've got a composition of components, so in this case, this is an example inspired from a supply chain ecosystem, a demand forecast combining with a supply forecast, combining with cost-based predictions, combining with a purchase order system, and you need to compose all these things together, and you want to ask counterfactual questions about whether you're composing them in the right way. Doing it with your production system is way too slow. So what you do is you introduce emulation, you introduce machine learning systems to look at those subcomponents, and if you have a good way of doing emulation that allows you to compose those emulators together, then you've got a much more powerful approach to running what we sometimes think of as a shadow system of your underlying production system. And this is with the aim of reducing the number of staff it requires to maintain and exploit a large deployed machine learning system, because that's a major barrier to, say, for example, two master students from Kampala designing, building, and deploying their own Uber-like ride-sharing system for the local boda taxi drivers. That's where the barriers are, that maintenance and explanation of the system. So that's kind of been the inspiration, and then it's got this sort of deep Gaussian processes as a potential way. We haven't got all this together, it's a very big project, but we think this is a very plausible way of imagining how to do these things in practice. That, and combine it in with a bit of causal modeling and causal emulation, as we call it. So just in terms of software, again, I think the other thing that we're really interested in, it relates again to what Shakir was saying. In terms of benchmarks, I think we're in an appalling position in terms of deep models that propagate uncertainty, because the advantages of doing this in practice tend to only emerge in deployment. And the sort of benchmarks where we say, oh, I just tried it on this data set, I just tried it on that data set, don't actually reflect the sort of utility of these sort of uncertainties. So who's to know whether it's deep Gaussian processes or deep neural networks or some other formalism that's the right way of going? I assure you, we certainly don't know until we start deploying those methods in practical applications. And I mean that sort of complex application like flying drones or whatever else. So this piece of software that we started on when we were at Amazon, but we've taken it out of Amazon and continue to develop it now, it's called EmuKit. And this is about trying to bring these type of emulation approaches together with complex real-world simulation-type ecosystems in one sort of software package. So it does things like Bayesian optimization, Gaussian quadrature, sensitivity analysis, these sort of things, but it's actually designed to be extended so to be a sort of platform for operating with these models that propagate uncertainty. So to sort of go all the way back to the sort of beginning, but with these images flicked around, I don't want to work in oil field anymore. I'm not a, but I think my inspiration personally for getting into the field was working in engineering domains. I was a mechanical engineer as an undergraduate. I did not start in machine learning because I wanted to solve intelligence. I wanted to solve practical problems that I saw people facing. And I really think that where we've seen, they're certainly not a universal solution, but I think that they provide a really interesting tool in that toolkit that we require to solve these real world problems. And I think one of the things that makes me proudest of the work that Andreas delivered is when you look at the breadth of application areas where people are deploying these methods in domains where it's quite hard to use the sort of classical methods, the sort of deep neural network things, because of due often with scarcity of data. So that was the plan. And then I just wanted to, Andreas said this is a slide he put in at the end without telling me. This was the group of us that took those techniques. And again, I like it because Andreas now has longer hair. And we started off with me having longer hair, that when we took the technology to Amazon and deployed it there, but now with all that experience, come out of Amazon again and deploying it in the real world. And thanks there, and I hope we've left time for we wanted good time for any questions, and I think we've got that, so I'll stop there.
So I think as people are working up the courage to walk up to the mic, I'll maybe start things off. So I've noticed that quite a bit of what came up in your talk is actually software systems, right? So you alluded to the connection between kind of deep GPs, the GP software and differential and probabilistic programming, and you're now working on EmuKit, right? So can I maybe ask you about kind of your experiences developing these systems? And, as someone who has a background in probabilistic programming, I'm of course a big believer in the fact that we should work on these systems. And maybe the question I'd like to ask you is, how should we evaluate these contributions as a machine learning community, right? Like, how do we make it so that, right, work on these systems can be recognized as a contribution that can help shape the direction of machine learning research?
Do you want to start, Andreas?
First of all, thanks to people like you who work on this domain, because we really rely on specialized expertise in probabilistic programming. These are not easy software to build, because you need the software expertise, but also understanding the science behind it. And this is a key difficulty, and that's why I think whoever works on that need to, of course, be credited and motivated. I think in certain conferences this has already been started to happen, like in NeurIPS. I think we have also presented, I think EmuKit was also presented in workshops in NeurIPS dedicated to software. And there is, in other communities like recommender systems, where I'm now, in the sense, there is also a lot of competitions that have to do with software. So in my opinion, doubling down on these efforts and bringing this element in machine learning conferences as well could be a direction. What do you think, Neil?
Yeah, it's something I've thought about a lot because I started producing software with papers, I think, much earlier than most of the machine learning community. And everyone in my team used to complain that I was forcing them to produce software. But I think I think a bit like the community thing, I think it's another way of forming community. I almost don't like the fact that it now seems to be a thing that people do and then say, oh, yeah, I did this, because it just means we've got a proliferation of these projects rather than, but you shouldn't prevent that. I don't have good answers other than it feels like it's the right thing to do, like forming communities and working with people. And it's clear with any system of reward that you're never going to reward the right things necessarily directly. And I think you just have to hope that in the long term, as I think we've just seen, in terms of the, standing here with the Test of Time Award, and like one of the things I'm trying to communicate is it's not about that paper itself. It's about spending that time with people, being inspired by other people, and, sharing your ideas through code and to enable them to do things, and then being inspired by the things that they do with it. And unfortunately, I think it's very hard for young students to sort of see that, because that can't pan out within the 3-year space of a PhD. And everyone's trying to tick the box of, I want a job with DeepMind or whichever else. But I think just to assure you that if you care passionately about this area, that indulging with that, I was at University of Sheffield for 15 years. It wasn't the place everyone wanted to go and be. And I had a brilliant career there. And you could do too. You can just be passionate about the thing that you're doing, and if you keep at it, then standing here today is like the reward, I think.
Fantastic.
Great, thanks both. Thank you for your timeline. I'm going to pull even further back, and I wondered how much kind of Nir Friedman's Gaussian Process Networks paper was part of the consciousness of this development. I mean, his paper was a fully visible thing, so there wasn't hidden layers, and he was caring more about structure learning. But from my point of view, it was the first time I saw kind of stacked Gaussian processes kind of leading into Gaussian processes. I don't know if that played a part, and I don't know if that also leads to the issue of whether or not, if we want to learn structures, these uncertainty-based methods can help us better in structure learning, or neural architecture search, as we might call it nowadays. I don't know if you have any thoughts on either of those.
Yeah, I sort of remember it. I think it didn't play a part. I mean, it was sort of awareness of it, but I think it was coming from, I think it's sort of like, oh, Nir Friedman's done the thing that I want. Oh, no, it's just observed. And then immediately, it's observed. It's like, oh, that isn't the thing that one was interested in. It's propagating the uncertainty. So I think when I heard about the paper, it was something that, oh, why, someone's done that now, because it was something I was sort of interested in. So it played a part in that regard, I suppose. But I think that the idea for me was already there. And, and Andreas will tell you I kept pestering him about it for a bit of time during his PhD before he switched on to it. I don't know, were you aware of that work?
Well, yeah, I think it's interesting. There could be like a universe where we reach the same, let's say, model through a different route. But I think the propagation of uncertainty to get like this composition is really what we were aiming for, right? Thinking out from the latent variable perspective. But I don't think explicitly we use that because of the reasons you mentioned, right?
One we haven't talked about that played a big part was Jeff Hinton stacking Boltzmann machines.
Oh, yeah.
In terms of just like, which is actually feeds into the hierarchical GPLVM directly. It's the same type of thing. And I remember, I think he gave a talk about that in like about 2001 at Microsoft or something like this, when no one was talking about deep learning and Jeff was doing it. Yeah, he really seemed to be trying to answer that question that David Mackay had posed. Maybe and it could be, well, Dave was a great follower of Jeff, so that question may have come to Dave Mackay from Jeff in the first place. Yeah.
Yeah, thank you for a great talk. So you actually commented on the connection of, deep GPs converging to neural networks, or that they're sort of a different class. Can you also draw the connection between Bayesian neural networks and GPs, and what kind of work has been done there? I haven't really followed that line of research.
You want to start?
Yeah, I mean, the connections that have been drawn by these researchers are assuming also distributions on the weights. So I think the connections are to an extent about Bayesian neural networks as well. But yeah, my hand-wavy intuitive explanation of that would just be that once you move to the Gaussian process world with the deep Gaussian processes, then you can do inference directly in the space of functions.
And I think to add, so I did in my PhD thesis, I worked on Bayesian neural networks. This is like 2000. And the reason I switched to Gaussian processes is, and I know there's much more sophisticated things, but the mean field approximations just weren't doing it. Because to get those really interesting, which is what I was using mixtures of mean field approximations in 2000 to get around the sort of lack of the correlated uncertainty that you often see in neural networks. And I haven't been following the latest stuff, but I find it interesting that already in those days we were seeing, I looked at Laplace approximation with Mackay, and I can see people are bringing that back into deep neural networks. But to be very honest, I haven't really, that community is thousands of people now, and it's just impossible to follow everything that everyone's doing. So there may be much deeper connections, and I don't really have anyone working on it myself. So there could be much closer things now. Maybe Mark knows. Oh, sorry, over there first.
Cool. Yeah, cool. So my question was the following. Like yesterday, we had a talk about carving out a niche as a sort of PhD students, I guess. And I liked your slide a lot, where you showed what work sort of fed into your research. So my question really is also a little bit for Andreas. Like, I mean, sometimes you have a sort of professor that has done a lot of work and he sort of feeds you an idea. And sometimes we had this issue from yesterday where you sort of want to carve out a niche as your own PhD student. So I was just wondering how it was for you, sort of how this sort of idea came about and how you sort of afterwards sort of carved out your own niche, I guess, as a PhD student. Yeah, thanks.
Yeah, it's interesting to answer this question because, of course, I have had just one experience, so I cannot compare with something else. I do feel that I was lucky in a sense, but one thing that Neil taught me, apart from all the deep Gaussian process stuff, was that you cannot really see someone else's path and try to follow it. So I never tried to do that. I just basically tried to follow up on the ideas that I found interesting. And at least in my case, in our case, right, Neil has this style of like trying to plant idea, and I think that's a good thing to do for anyone who's like a supervisor. Try to plant ideas in students' minds, but not like say, hey, do that. I guess also showing trust in the student that they can come up with their own interpretation of the idea. So I think that's how, at least from my perspective, we ended up with this work. Basically discussing, I think Neil had something a bit more specific in mind than what he was letting me know, just to see also my perspective, and we were discussing, and that's how we converged, basically. That's how I perceived it, at least.
Yeah, just from the supervisor's perspective, I think it becomes increasingly hard, and it's a transition in my career. I mean, you can almost see my career mapped out here. All the stuff on the left is the early Gaussian process workshops. A lot of that was reported at. And it's a really interesting transition in my career where I guess my name was becoming more widely known and I was getting very, very good students. And it caused me to have to start taking more of a step back to give students space. And I was quite conscious about that because otherwise you start feeling you're competing with them for intellectual ideas. And my own approach was to introduce, and Michalis was great on this stuff as well. And Carl-Henrik Eck, who is a former student of mine, worked with Andreas a lot. So my own approach is to start bringing in other people whose ideas I respect, and I'm pleased that Andreas, maybe he says that because he thinks that's what I want him to say, but never planting the idea too precisely in the student's mind, because then it's not a collaboration, you're not allowing them to bring their own piece to it, but it's quite a slow process and requires patience, and I think that it's increasingly hard for people, both the student and the supervisor, when like people are now expecting to come out of their PhD with multiple papers. I mean, bear in mind, I graduated my PhD with I think one Europe's paper, and I think maybe I got one AISTATS shortly afterwards. And you get people applying to PhDs with that stuff now, applying to master's programs with that stuff now. So that's made that very difficult, I think.
Can I add to that? Sorry, because I also want to call out Michalis, Carl-Henrik, Carl-Henrik, I work with those. And to complement my answer, I think it's also important when the PhD supervisor also plays a bit the role of the people's manager, right, and how to build a team. So very often Neil was like, hey, here's Carl-Henrik, I introduce him to you, go have a coffee or do a visit, things like that. And this also played an important role for these ideas to grow in a collaborative way.
First, I want to say congratulations on the award. I'm very pleased that paper got the Test of Time award. You talked about community, and so 10 years ago, the machine learning community composition looked a little bit different from today. And I wanted to have your thoughts on maybe what the future of Gaussian processes, in particular with, I would say, more like a stagnant community size, looks like in that field of machine learning.
Do you want to start? Well, I first of all want to start by congratulating Fran and Jennifer and Jan Willem on demonstrating how you can pull together a hybrid conference, which gives us all that community feel in that modern era. And, you know, we were talking about it last night with yourselves at dinner. So I definitely don't think that goes away. And I also think I like working with Gaussian processes. You know, they're really interesting models, but I think we should constantly not presuppose that they're the right way of doing things. You have to have faith in the methods you work on a bit, because otherwise you're never going to put anything into them. But you can see the way I'm personally trying to deal with what is quite a vast community and difficult to stay on top of things is to try and identify the type of problem sets other people aren't looking at and use them to increasingly steer what I'm doing. And I was sort of recognizing that as well in Shakir's talk this morning. I think that he was doing very much the same sort of thing and encouraging us all to think about that way of doing things. If a technology is successful, it will prove its worth in applications, and there's a number of ways in which you can support that in terms of the software, the community building, the surfacing of those applications back into your core community, and a number of other things that I'm forgetting about. But again, I want to emphasize that I appreciate this is the privilege of the aged, as it were, in terms of you've already established a reputation. You can sort of play and do these things. But having said that, I was doing it right from early career. But I think I was just in an environment where, and at a time when that was possible. I don't know to what extent it's possible nowadays. I don't know, did you have you probably have a very good answer, Mark, as well, so I should ask you to answer your own question.
We can take that offline.
All right, so walk to the mic. So if there's no more questions, let's thank Andreas and Neil again and congratulate them.